So I'm Tim, and this is joint work with Michael Homer, James Noble, Kim Bruce, and at least conceptually also Andrew Black as well, of the GRACE Research Project. And I didn't really want to talk about GRACE because this paper's not really, it doesn't really talk too much about GRACE either because it's not the focus of the paper. But GRACE gives us a reasonable context into why we would want to look into what we looked into. And part of that context is this idea of objects versus classes. And I've occasionally presented this more as a conflict between Andrew and Kim on the design committee. So we've got Andrew v. Kim, sort of dawn of justice. We've got the battle of the titans. But this isn't actually really reflective of everything that they stand for, certainly. So we'll boil that down into really what the key conflict that Andrew and Kim have had on the design, which is this idea of objects first versus object draw. And those seem like two very different things, because they are. One is a very sort of almost an ideological position that we don't need classes, that a language should be objects first, and that the object should be self-describing. We don't need classes to describe objects, and it would be simpler to get rid of them. And we're always keen to get rid of things in language design. And so the counterpoint to this has been, at least for us, this library called Object Draw that Kim has. And it was written in Java, and it's for helping students get going quickly using object-oriented programming to draw things on the screen. And it turned out that a lot of the implementation of Object Draw relied quite heavily on the semantics of inheritance in Java. And so when we were designing this language, and they began with this objects-first design, and we saw some of this this morning. The idea was that we could use delegation and be done with it. That would give us everything we needed to do because that's object inheritance. And it turned out to be not quite so simple because there were so many semantics that were sort of embedded in this idea of class inheritance that delegation didn't support, that we had to think more in depth about what we actually needed to do to solve this problem. Right, because this problem is solved, right? Dave Ungar, in his infinite wisdom, 29 or so years ago, solved this problem for us when he invented delegation, or at least implemented self with delegation in it. He said, here's an object, and it has a parent pointer, and so if we send a message to this object and it doesn't understand, it can send it off to the parent. And then if we want to do something like classes, well, the parent pointer just points to some new object. Right, so this factory is essentially a class, and the call to new is like the super call. So this problem was supposed to be solved, and we'll see why maybe not so much. The context of this talk, at least the syntax of the examples, is going to be in GRACE. So here's just a quick introduction. We've got a method called graphic that returns some fresh object. So that object expression actually constructs a new object that's self-describing. And over here we've got an Amelia object which inherits from it. Any features that Amelia doesn't support, a graphic does. Amelia can ask this graphic object to implement for her. So the real question is, well, what does it mean for Amelia to say she will inherit from graphic, this call to graphic specifically? And so the real question is then, do our inheritance semantics, does the semantics of this part of the program actually allow us to implement classes in the way that we expect, and implement class inheritance specifically? And so the idea was, well, let's look at a bunch of different object semantics, object inheritance semantics. And so some of the stuff that we're going to look at was actually implemented at various times in GRACE, and some of them are just more foundational. Here's how object inheritance has worked at some point in various languages. And so we did that, and there's some stuff going on in the paper, and it gets a bit hairy near the end, and eventually it falls off the bottom of the slide because it's sort of gotten a little bit too hairy. But we're not going to talk about that because it's way too hairy. Although if we have some time, we can look at some of it. The main thing is you can also find is as an artifact, and also if you're quick, you can follow along with this talk. You can grab the semantics implemented in PLT Redux and check that everything does what we said that it does. And so here's what we're gonna fill in as we go along. This table we've got on the down the rows are the models that we're going to look at, and across the top we're going to sort of motivate some concerns that we're looking at as well. And the idea is that there should be one solution to this problem. We should be able to find one of these things that we're going to look at and say that solves our problem. And we've got Java going along the bottom as sort of like a comparison. And we'll see more about what those concerns are later. So, what does it mean to have object inheritance? Let's start by looking at the really foundational models of object inheritance. And we identified three that we were going to look at. One which was forwarding, similar to the way that E works. One which is a delegation, which is a bit like which is what JavaScript itself claimed to use. And then also concatenation, which is something that was in the Kiva language. So first we'll look at the semantics of forwarding, right? And we should have a fairly good idea of what this is going to do, because it's really the simplest semantics that you could come up with. You've got two objects, A and B inherits from A, and all that means is that if a request comes in to B doesn't know how to handle it, well, it just punts it up to A. And there's no special semantics going on here, it just sends another message to A. And it's essentially just a form of reuse. It means we don't have to re-implement stuff, re-implement these specific forwarding methods in B. We just say essentially there are a bunch of methods in B that go off to A. It's just exactly the same. And this gives us a problem because arguably it's missing the sort of main feature of inheritance that you might expect, and that's that we can't do down calls. And that means that we can't override methods because when that call goes up to A, the context continues as though that call had gone to A originally. That if there are further self calls inside of A, B is not involved in that process at all anymore. And so we can see that in the example we saw before in a bit more detail. So here Amelia is inheriting from Graphic still, but now Graphic has a draw method and an abstract image method. And the idea is pretty clearly that that the inheriting object should provide an implementation of that image method. And so Amelia does that, but under forwarding, unfortunately, draw still doesn't work because this call to image ends up going back to Graphic again. And so we end up still hitting the abstract method and getting some sort of error, depending on whatever our dynamic semantics for abstract methods are. So delegation is sort of like the standard semantics of object inheritance because it allows us to do method overriding, and it gives us down calls. So same relationship again, we've got A and B inherits from A, and a method comes into B, doesn't know how to handle it, punts it up to A, and now there's the semantics of this call say that any call to self inside of A during this request is going to be sent back down to B. So the value of the self variable and also for implicit calls, it should be interpreted as the original receiver of the request. And that allows us to do down calls, it allows us to override methods, and allows us to do the standard sort of reuse we see with classes. There are some problems with this approach. One is that you have this vampire problem, this idea that any object can take any other object and sort of possess it from the outside and set it off to do its bidding. It makes it kind of difficult to do local reasoning because methods that you might inside of an object that you might expect to be local to that object can always be overridden by some other object. And there are interesting security problems there as well, where what does it mean for something to be protected in a language where we don't have classes, and any object can always extend any other object? Does that mean that it's not really protected because you can always get access to it through this inheritance mechanism? The other problem with delegation is it's kind of surprising if you're used to classes. This is a problem that a lot of people have seen in JavaScript, where there's shared mutable state throughout an inheritance hierarchy. And we've called this action at a distance. So here's this really simple example. Again, Amelia and Graphic. This time Graphic has a name, and Amelia inherits from a pre-existing instance of this call to Graphic. So we've called Graphic already. We've given it a name somewhere else, and then Amelia inherits from it. And then Amelia sets her name to be Amelia. And the problem is that if there are any other objects that also inherit from parent, you've just set all of their names to be Amelia. And if they also set their names, then they set Amelia's names to be whatever they need to set to. We can see this in self as well. So we've got two things going on here. First of all, we can see that we get down calls. We've got an object above, which has a run method that calls does a self call on say, and we've got a say method in both cases below overriding say. When we run on below, we get printed out below. So that's sort of evidence that the down call is happening. But also, if we set the value of below, any shared inheritance hierarchy, it also sets the value of all of the shared children of that parent. So the value of other becomes 5 because it's set in the initialization of below.
Yeah. So is this like if you forgot to do the copy down, this is what happens?
Yeah. So basically, the idea is that this behavior isn't wrong. It's just that if you're expecting it to work like classes, that when you do inheritance, there's no shared state with any other object, that they're sort of all merged together into a single object, then that's not what happens. And so if you can get really easily confused about that if you're used to classes. And it's good that you mentioned copy down, because that's the next model where we say, hey, we're going to avoid that problem by actually just copying everything in the object. So here we've got this sort of conceptual object that hasn't really been initialized yet, or constructed yet, because the inheritance hasn't happened yet. So it said, we're going to construct this object, but it's inheriting from A, and we're not going to keep that relationship. We're just going to we're going to copy all down all the stuff out of A into B, and then sever that relationship. There's no longer any relationship between A and B. And that means that changes to the inherited object are not reflected in the inheriting object. And again, this isn't necessarily good or bad. You might want this to happen, and we saw a bit of this with in James's talk, where there was an object was updated on the fly, and the other objects that were inherited from that weren't updated to reflect the problem. So one of the problems that all three of these models have, and it was really the motivating factor for us moving away from having object inheritance, was this problem of registration of self during initialization. So here we got back to our example again, and all that happens is during the initialization in the super object, we store the value of self somewhere. And the problem is that under all three of those models, we've just saved the wrong object. Or at least, assuming by this example, our intention was probably to save Amelia. Right? In fact, when we inherit from graphic, it's not really necessary to even create this object over here, because it's just there as a form of reuse. So we started looking at cases where we wouldn't end up with this hierarchy of objects, that our inheritance would work to merge together all of the definitions that you were trying to inherit from. So we came up with essentially two different kinds of models. We first had merged identity and grace, and then eventually moved on to this other thing called uniform identity. And they sort of loosely correspond to C++ semantics and Java inheritance semantics. The main difference in terms of how you can use them from the last three models is that you can only inherit from calls to a method, and in particular, that has to be a fresh object that the method returns. You cannot inherit from a pre-existing object. So, under merged identity, the idea is that the inheriting object becomes the inherited object. It essentially sort of steals the identity of the object it's going to inherit from. And the idea is that you still have this registration problem where you save the wrong object, but after the inheritance occurs, that's alright, because the inherited object steals that identity, and it essentially replaces itself in all of the cases where we've saved it. So again, we've got this conceptual object here that hasn't quite been constructed yet. It's inheriting from A, and instead of establishing these two different objects, what we're going to do is just mash everything that was going to be in B into A. And yeah, so this avoids that registration problem by saying there actually ends up being a single identity for all of the objects. The obvious problem with this is that there's sort of a body snatchers thing going on here. And that's the main reason why you can't inherit from a pre-existing object in this model, because it would be a security nightmare. That at any point in time, you could steal the identity of an object and change its implementation. There's also the problem that you have in C++ where objects aren't stable during construction. You can observe the structure of an object and the implementation of an object change over time. So we can see that here, during the initialization of graphic, we call this image method, and image is overridden in Amelia here. But the problem is that because we call image during initialization, this overriding method hasn't been applied to the object yet. And so the image call during the initialization ends up still going to the abstract method. It's only after the initialization that this overriding that applies that a call to image will correctly go to the right place. And so uniform identity is sort of the final model that it was aiming to solve that problem. And the main problem with it is really that it's kind of magic, more so than any of the other ones we've seen so far. It's a lot harder to describe exactly what's going on compared to the other ones. So here we have an object B, and we've constructed it. It has this identity B, and it has that object has these methods in it, but it's not initialized yet. We don't initialize it. We're waiting for this inheritance to occur. So we go up and we evaluate to some object expression up here, and before we evaluate that object, we kind of do something similar to merged identity, except instead of going up, we go down. So we bring down all the methods that we were going to inherit, and we still haven't run any initialization code. And this is one of the big complicating factors in this model is that if there are multiple stacks of inheritance, we have to process all of those stacks. All of the previous models, we could do 2 objects at a time. This one, we have to hold on to the initialization code until we get to the top, and then once we've established the entire construction of the object, we can initialize it. This means that the initialization code runs in the expected context. You can still see uninitialized state during construction, though, which is just like in Java. So none of these are very satisfactory as foundational models. They're not really full object inheritance, but they do give us what we were looking for in terms of the expected behavior. So it's worth just quickly looking at how some other languages do this, because we know that we can do something that pretty much simulates classes in JavaScript. And the reason we can do that is basically because JavaScript is kind of crazy and allows you to do a lot of different things. And also because the object inheritance in JavaScript is based around constructors, not about direct relationships between objects. So when we say above.prototype.run and below.prototype say, we're not setting the prototype of an existing object, we're setting the prototype of a conceptual class of objects. So we're essentially establishing a relationship between a class and an object, not 2 objects. And then the only reason we can get the uniform identity semantics is here, where we can set the value of this variable in the call. So essentially, this gives you the uniform identity semantics. In E, you have a really, really nice way of doing this because you can't even see. You get a uniform identity, but you can't even see uninitialized state. It's really great. And what happens is you have a function that takes the self identity. And you get to say, during the extends clause, you get to refer to the object you're creating. The problem with this is that what gets sent up is a promise. And specifically, it is a promise that is going to resolve into the object that is inheriting. And that's a really, really specific to E. And so the problem is, this is great, but only really Mark Miller can use it. So we've done multiple inheritance. We've also done a series of method resolutions, method conflict resolutions. And the problem is that we get to this table and there's nothing really that is entirely green all the way across. The registration, the down calls, the point is that there's no good solution that solves all of these problems. And the other problem is that this is kind of a factor, like preferring one over the other. So the problem is that the table could also look like this. And so really what ends up mattering is that you need to think about what the design goals of your language are if you're going to try and pick one of these semantics. That you have to decide which of those columns that you prefer over others in order to decide what the right answer is going to be. And so what can we learn from this? Well, for our language designers, Jonathan in particular, the problem is that simple foundations don't necessarily give you a simple design. If you strip away a lot of stuff and you want to get back to some sort of functionality, you can't always recover that. For everyone else, well, there's still problems hidden in solved designs. We thought that this problem was easy and solved, and it turned out that it wasn't. Thank you very much.
Time for a couple of questions.
Could you expand on the reasons the E design?
Sorry, I kind of lied before. Mark Miller is not the only person who can use it. You can all use it. The only reason not to use this would be because you don't want to use E for some other reason.
No, I'm not asking, could you expand on reasons not to use E? I'm asking, why not use the E style of inheritance in Grace?
Well, you would need the promises. And so then the answer is, well, you just put promises into the language as well. And the problem you have then is that, well, you've kind of swapped out classes for these promises. It's specifically these promises that resolve into their thing. So from a conceptual level, the idea was to strip out as much as possible and to put something else back in to solve that problem is sort of against that idea.
So one of the things that surprised me in looking at these alternatives was that immutable objects, which I'd always thought as a big simplification of the OO model, make this all very much harder. And you didn't really talk about that.
Yeah, mostly because we didn't really look at it too much in the paper. I mean, there's a lot of really interesting complications that come out from this. Like I was saying with access control as well, that what does confidential mean in the delegation model, for instance. So there's still plenty of space that we haven't really gone really in depth into. Was there something specific about the immutable objects that was particularly problematic? Well,
because initialization, the whole point of an immutable object is that it's created already initialized, and the semantics
you can see
defers the. So there's no such thing as an immutable object because you can see it being changed from uninitialized to becoming initialized.
Yeah. Again, there's no really good answer to this problem.
I was wondering two things. Uniform identity, does that reflect the class-based approach or the Java approach? That's my first question. Second question, I think that in general, thinking of things as copying and merging is a nice approach. It simplifies things, it flattens. So I would have thought that another criterion in your matrix would have been how many pointers are left in the system and how much, and instead of pointers, do I have flattening?
Right. So that's, yeah, I guess that wasn't a column in the table. But that was different. So the issue was that we couldn't really find a trade-off between you have a bunch of these objects left around when you're working with classes, and you can also inherit from pre-existing objects. And so the pre-existing objects column sort of handles that, but that could be something to look a bit more in depth. And what did you mean between Java and classes?
I thought that uniform identity reflects how inheritance works in Java with classes.
Yes.
Does it reflect it in all aspects?
I mean, no, there's obviously a significant amount of complication going from that to Java. It's mostly the initialization semantics that we were looking at.